So here's just her more pictures from what she was just talking about. You can see over on the far side how the original on the top got smaller when it gave its electron away because it dropped down the energy level, and then over here on this side it got bigger because it added that extra electron and couldn't keep it close. So it's kind of spread out weird, but what is missing? Who's not on this table? Hydrogen's not, but what else isn't? Noble gases. They're not on here. They don't count for periodic trends. Because why? They already have 8. They don't care about bonding. They don't care about giving their electrons away. They're going to keep them all close. They're not going to let them go. And we'll talk about that a little bit more later. So your atomic radius is the distance between the nucleus and the outer edge of an atom. The distance between the nucleus and the outer edge of an atom. So we've heard radius before in math class, so now we're just adding it to our atoms. Kind of like we did the last week or two with the bond length and energy and stuff. So if the atomic radius is the distance between the nucleus and the outer edge, then we can see it change from period to period. So period goes which way on the table? Horizontal, yeah. So each period has a new principal quantum number, which represents the energy levels. We talked about that when we looked at light. And the larger the n, so the larger the quantum number, the larger the radius. Right? So I mean, the more energy levels, the larger the radius is going to get. And so we can see that here. We have 4 rings on the left and 2 rings on the right, so we know this one's smaller. And so on your table, this is the trend. This is the actual trend that you're going to see. So they increase as we go to the left and down. So you'll want to draw your arrows on the table under there. So I got the arrows up here for y'all. And so why does it increase going down? Why does it increase going down? It has more energy levels. The quantum number is increasing. Right. Why would it increase to the left? Why wouldn't this side be bigger?
Because they are losing.
They're gaining. They're getting. But you're right on the difference. Yeah. They're losing them, right? They're trying to lose it, and then they get bigger, right? So we said right. That's good. Okay, so here's a little bit of a picture that you can better see it. And so you can really see the size moves. So let's do an example. Who's going to be bigger? Fluorine or aluminum? Who's bigger? Aluminum. What about beryllium or calcium? Calcium. Alright, y'all got that. That's pretty easy. Alright, so the next thing we're going to talk about is ionization energy. The energy required to remove an electron from an atom. The energy required to remove an electron from an atom. So you can think of this like a price. How much are you going to pay to take that electron from somebody else, to get it for yourself? How much are you willing to pay to get that electron. So if our ionization energy is the energy required to remove an electron, then we have different stages. I mean, you have more than one electron. So you have your first ionization energy. So the energy required to remove the most loosely held electron from an atom. The most loosely. I know Ms. Martindale was saying that you need to look at the spelling. She's getting a lot of spelling issues with the word lose and loosely. This one's got double O in it. So it's loosely held there. So this is where, I mean, if you're shopping around, you have different prices at different stores, but I mean, you're always going to look for the cheapest deal, right? You're always going to look for the cheapest electron to save. And so, next page, it's going to be measured in kilojoules per mole.
Martindale,
Yes, ma'am.
Noah Fallbush, and Avery McAvoy.
Okay.
Thank you.
I don't know. I guess go off. I don't know. She did. I don't know what that means or.
They called you. Go on, get out.
Noah, go see. I don't know what to tell you.
Okay, this is like the hardest section we've done yet, and I'm not about busy.
We'll have
Let
time.
me call and see if they can come later. Let me call and see who.
That'll work.
We were supposed to.
Avery was already left.
Oh, it's good.
Hang on, let me see. But
Ooh.
Noah, somebody called Noah and Avery to the office when we were wondering if we could finish our notes and then send them, or do they need to come now?
No, you finished. That's fine.
Because we weren't even sure who called them or where they're supposed to go. So, okay.
Just finish what you're doing. That's fine.
Thank you.
Okay.
Okay.
All right, so,
Come on.
all right, ionization energy. You measure it in kilojoules per mole. So that's your first blank. And then it increases as the atomic numbers increase. So, I mean, we know that goes left to right like you're reading. And so, as it increases, the ionization energy increases. So this is a little different than, the directions are a little different than the atomic radius. Because it increases up a family. So going up, it increases. And y'all can draw your arrows on your table there.
Well, we can for when she gets here, we'll take them off, we'll take it off, we'll hang it to the board, and then usually with some magnets, now you can put magnets on those and you can just, it's real easy, because it'll stick to the board. We'll fix it at lunch. That'll make it quicker for you.
Alright guys, so y'all got your arrows drawn? Alright, so metals. Let's talk about metals. They have a low first ionization energy because they have a positive charge and need to gain electrons. No, I read that wrong. Need to lose electrons, my bad. Alright, so they're trying to get rid of that one so they can shrink down to their 8 valence, right? So they want to get rid of it. They don't want to be putting a real high price on their electron. So they have garage sale prices. They're just selling it to get it out of their house. Y'all have stuff like that? I have plenty of stuff that I just want to put $1 on and get it out of my house. And so that's That's how your metals are. They're not going to have such a high price because they want to let them go. But non-metals want to hold on to what they have and they want to get more. So they're going to have a high burst ionization energy because they have a negative charge and need to gain electrons. So that's a typo on your note sheet right there, where you fill in non-metals have a high burst ionization. It says low, so you need to scratch that out and write high. So make sure you got non-metals have a high ionization energy because they have a negative charge and need to gain electrons. And so their prices, they're going to be like brand new in the store prices. They ain't going to let that go for cheap. And so here you can see like 3D how it increases. It increases going up and it increases to the right. And so you can see the noble gases, see how much higher they are from the others, because they're not going to bond with anybody, because I mean they're the noble gases. They have their 8, they're perfectly happy. They're not interested in selling or buying or anything. And so other than them, you can see fluorine is going to be our highest. So fluorine up in this corner is our highest, and then francium down here in this corner is going to be our lowest. Alright, so like we said, we've got a first, so obviously we're going to have second, third, fourth, and fifth. We've got a bunch of ionization energies, and so as additional electrons are lost from an atom, you can measure their other ionization energies as you go. And so the energy required to remove the following electrons from aluminum are listed like this. So we can see this increase. It's going to increase every time. So from the first to the second, it's going to increase. To the third, it's going to increase. To the fourth and fifth, it's going to increase. But we're going to hit a point that you jump. See how big a jump this is? 500, 1800, 2700, 11,000. See how much we jumped? So you're going to have to recognize where to draw that line on some of your problems. So where is aluminum? Aluminum's here. Why do you think it takes why do you think after the third ionization energy it jumps so high? Because it's got a +3 charge. It has 3 electrons that it can lose. Right? It wants to lose all 3 of those. Once it loses all 3 of those, it's going to shrink down to its 8 valence. And it's going to be happy again. It's not going to need to do any more. It's not going to want to lose anymore, so it's going to put its price way back up. These first 3, he's okay with selling those. This fourth one, he's not going to be giving that away. And so here you can see that on several different elements. So the first one, sodium. Where's sodium on our table? First column, what's its charge? +1. So after the first ionization energy, it's got a big old jump. Magnesium is 2+. Aluminum is 3+, like we just saw. And so you can see, as they lose, then you can see where to draw their line. Y'all catch the big jumps? And then y'all know here at the bottom with like argon, you don't see his big jump. He's pretty steady because he has all 8. He's just not going to want to let go of any of them. So, I mean, it's going to continually increase, but if there's not a drastic increase, then you don't have that change like that. Alright, so new topic. Electronegativity is a measure of the ability to attract electrons within a compound. So it's the measure of the ability of an atom to attract electrons within a compound. Our little picture here is kind of showing a little tug of war game. That's what they're doing. It's within your compound, but it's still a bit of a tug of war. You got that? No? So, a measure of the ability of an atom to attract electrons within a compound. So, in the compound, the negative charge of the valence electrons is usually concentrated closer to one atom than the other. Like even in covalent bonds, even just between nonmetals. So, I mean, we know on covalent bonds we can have polar or nonpolar, whether it's sharing it equally or non-equally. So, on the right here we have nonpolar, so we know that's shared equally. You can see the concentrations on both sides. But on our polar, y'all know the polar, where it stays a little bit more on one side sometimes. It's unequal sharing, and so it's a little more concentrated. It's not like ionic. It's not fully like positive or negative on one side. It's just, it kind of lingers over there. You know, you walk by something, you're just kind of looking at it a little extra long. It kind of just looks over there a little extra time. And so that's how we see our unequal sharing of the electrons in a polar covalent bond. And so that's how we see the electronegativity in our compounds. And so electronegativity increases just like ionization energy does. It increases up and increases to the right. So fluorine, again, is our highest electronegativity. And so you'll want to draw your arrows for your periodic table for this one. And once you get your arrows drawn, you can flip over to the next page. Remember, we're still not including the noble gases. They still don't care about any of this. So on the next page, on the top, you're going to fill in your most electronegative elements. So fluorine, we said, is the highest, but these others, they like to bond just a little bit more. So oxygen, nitrogen, fluorine, they're a little bit better at this tug-of-war game. Alright, so if these are the best at this tug-of-war game, who is going to be the worst at it? Who is not going to be strong at this tug-of-war game? Alright, so this was a little funny. I forgot about. Chemistry cat came back again. And so fluorine, it doesn't want to bond. Alright, so on your question on your notes, what are the least electronegative atoms? Who is the least electronegative? Alkali and alkaline. So your first two columns, your +1, +2, they're the least electronegative. They're trying to get rid of their electrons. They don't want to get any more. Because, I mean, they have to get 7 or 6 more rather than just losing 1 or 2. It's going to be easier for them to lose 1 or 2. They don't want to attract anymore. They just want to get rid of what they already have. Alright. So for your problems, on each of your types of bonds, you're going to want to draw your pictures for these. They're kind of in backwards order, so your first one's ionic, polar, and then nonpolar. So make sure you get those drawn in the right spots. And so that you can just really see that ionic bonds are not sharing. We know that in ionic bonds, sharing like this. And so polar they're sharing, but it's a little more on one side, and then non-polar it's equal. So that's what you want to make sure you picture. Now above it is how we measure it. If you subtract the differences in electronegativity, it's going to determine, you can determine whether it's going to be ionic, polar, or nonpolar. And this is already typed down below for you, but you're going to need to be able to determine. Oh, I clicked it. Okay,
Yeah,
guys.
hit the up there, yeah.
Yeah, I did it. All right. So right there above it is, so if it's 1.7 or greater, the distance between the two electronegativities, if it's 1.7 or greater, then it's an ionic bond. That's going to be this one. If the difference is from 0.3 to 1.69, then it's going to be polar. It's unequal, and so it's going to be polar. It's going to be the middle one. And then if it's less than 0.3, then it's going to be nonpolar, because it's really equal. It's really kind of neutral between the two on how they have their electronegativity distributed. So get your pictures filled in and make sure you know how that relates to your numbers below. And you're gonna have problems where she's not gonna give you the like, she'll give you two elements. So she'll give you like calcium and chlorine, and give you the electronegativities, and you're going to have to subtract them and decide whether it's ionic or polar or nonpolar. She's not going to give you the elements, she's just going to give you the numbers. So you're going to have to do a little subtraction for this. Because if she just gave you the elements too, then you'd know, oh, if it's a metal, then it's ionic automatically. But that's too easy. You already know how to do that. Alright. The last thing, this isn't on your sheet. You can just write it down at the bottom. It's your fourth trend is oxidation numbers. So you've already been working with these. You know what these are. You just need to memorize them. So you know they're +1, +2, +3, +4, -3, -2, -1, 0. You know what they are. You just need to have them memorized for this. And so you know your oxidation numbers are how many electrons an atom will gain or lose to fill its outer S and P sublevels. And you know if it's a positive charge, it wants to lose electrons. It's going to lose them, like our metals do. And if it's a negative charge, it's wanting to gain more electrons. It's wanting to add a couple more so it can be full. You got that? So that'll do it for our PowerPoint.